orbital energy, and the value is it's the reciprocal of the original semi-major axis. So how we determine that is we take the observed orbit and we integrate it backwards in time to before any planetary perturbations could have altered its orbit. So this is around 250 AU from the sun is usually where we integrate the orbit out to. And when this is done for a large sample of comets, you can see a spike in the distribution at very large semi-major axes when the semi-major axis is greater than 10,000 AU. And this spike here is what led to the postulation of the Oort cloud in the first place. This is a figure from like the original paper that postulated the Oort cloud showing this spike, which is called the Oort spike is what we call it. So historically, comets that are within this spike are considered dynamically new. That's what has been used for many decades. However, recent work has shown that in reality, not all of the comets in this Oort spike are truly pristine. So some recent studies by Dubzinski and Krolikowska in 2015 have shown that essentially like half of the objects in this Oort spike have had previous perihelion distances less than 30 AU. And at 30 AU from the sun, and within 30 AU from the sun, you can have carbon monoxide can sublimate that close to the sun. So they have experienced some processing. So we can't say that everything in the Oort spike is super pristine. Furthermore, just getting the value of 1 over A naught takes a really long observation arc that has to be very accurate, which is also hard for comets because they're so nebulous. So it's difficult to even get that original reliable measurement to begin with. So altogether, this would mean that it could be super beneficial to have some discriminator of dynamical age outside of modeling. And so the question that I want to ask, especially as an observer, is can we use observations to tell the difference between new versus returning? And we do actually expect them to be different observationally, because if they've had several solar passages near the sun, if they are processed, we would expect them to have different volatile inventory. And when I say volatiles, I'm mostly meaning ices that are sublimating. So I mean mostly CO, CO2, and water are the main 3 volatiles in comets. So those are the ones that I'm generally referring to. But we expect, but there's more than just those 3. So we expect to have different volatile inventory if some of these ices have been sublimated on a previous passage. Also, if the ices have been sublimated from a surface layer that would leave maybe this potential like dust mantle we might expect for returning comets that new comets wouldn't have. In general, they could have just a totally different formation region because they are maybe in different places of the Oort cloud, different paths to get to the Oort cloud, some of these objects. So looking at them observationally does make sense. This has been looked at spectroscopically for a few comets, and a study that came out in 2022, which is what this figure is showing, is that surprisingly, new comets have less CO than returning comets. And I say surprisingly because CO is more volatile than CO2, meaning that we expect a new comet would have retained that more than a returning comet would. But we see actually the opposite. So in this figure, you see on the further left that's where it's in the Oort spike, and those objects have a lower CO to CO2 ratio than the other ones. So maybe we could use this CO-CO2 ratio as a diagnostic for is it new or returning. But as you guys are well aware, we can't get spectroscopic observations for a large number of comets very easily, especially CO2, which can only be observed from space-based observatories directly. Um, so one of the questions is, can we use photometry, which can be applied to many comets? Broadband much fainter. We can go to smaller facilities and have more observing time because it's less competitive. So what could photometry tell us about new versus returning comets? So traditionally, there is sorry, I don't know if you can hear my dog barking. Um, so traditionally, we do see a difference between new and returning comets in how they brighten using broadband photometry. So I'm showing that here. Basically, we use this parameter called an activity index, or N, which you can think of as what is the slope of brightening? How steeply is the comet brightening, which is related to its activity level. So historically, and these are studies from several decades ago at this point, found that new comets, so comets that were within the Oort spike, have a more shallow brightening slope than returning comets, which have a more steeper brightening slope. So this traditional model has been used for, like I said, characterization. When we're looking at a group of comets, we can use this value. It's also used to predict future brightness behavior. So when we are looking to see how bright a comet will be when we're setting up our observations, we use this model fitted to the past observations, and we project that forward closer to the sun to get an idea of how bright the comet will be. However, the big caveat here is that these studies and this model originated with comet observations that occurred within 3 AU from the sun. But now we can discover comets much further out, much further than 3 AU from the sun. And this 3 AU from the sun is an important cutoff here because that is where water ice sublimation, which is the most abundant volatile that we see in comets, that's when water ice sublimation is really driving the activity within 3 AU of the sun. So now we're discovering comets much further away from the sun, as you can see in this figure, frequently beyond 5 AU and even sometimes beyond 10 AU. So the question that we want to ask is, will this model hold true across a large range of heliocentric distances, so more than just a short range? And then also, will it hold true just in a totally different regime where water ice sublimation is inefficient? And this is also important too, because at this, beyond 3 AU from the sun, the drivers of this distant activity are much less understood than the water ice sublimation near the sun. So having these observations and getting an idea of how they brighten can tell us more about what is driving the distant activity that we don't fully understand. So if water ice isn't driving activity beyond 5 AU from the sun, 3 AU from the sun, so what is? And there are 4 categories that I can think of that are the main ones that people talk about. The main 2 being CO sublimation. So CO sublimation can happen tens of AU from the sun. It is the most volatile of the abundant ices, like I said, of CO, CO2, and water being the most abundant ices in comets. The other one being CO2 sublimation. So this can start becoming active in can be comets can become active in the teens, early, 6, 10 to 15 AU. And this is consistent with a lot of those discovery distances that we saw before. But the question is this actually when a lot of comets are like turning on, or is this little cutoff the limits of our current surveys? So I'll just show you again. So you can, I'm sure many of you guys noticed this sort of like ridge here around 10 AU to the right. So yeah, we're not sure if that's a real ridge or if it is just due to the limits of our surveys. But if it was actually real, that would probably be consistent with CO2 sublimation. Another potential driver there in this region is a one-time transition for water ice to go from amorphous to crystalline phases. Though it's expected that this would be more like a large surge or outburst. And there hasn't been a lot of study on how to like distinguish that photometrically specifically. Some ideas are talking about a volatile frosting. So there can be some basically surface level ices deposited in the Oort cloud, which would then be just very quickly depleted after a first perihelion passage that we would expect to see some distant activity from there. All right. Another thing to think about when we're talking about distant comets is when we have more distant discoveries, we need better predictions. So estimating this future brightness is not trivial. I made it seem like that, I know, like 3 slides ago when I was talking about we just follow this line and then we say how bright the comet's going to be. Comets brightness can change dramatically throughout its orbit for many different reasons. There's frequently been these ideas, and I show an example of an old article. This says, oh, this comet is going to be like visible to the naked eye. It's going to be like a super bright comet next year. Everyone's going to see it. It's going to be crazy. And 90% of the time, it does not actually happen. But so we don't want many of these press releases saying that falsely if we can help it. So having a better brightness estimation is critical for just telescope proposals to know how bright the comet's going to be, mission planning, and also, like I said, press releases like this one. Predicting brightness behavior is particularly important for the upcoming Comet Interceptor mission. So the Comet Interceptor mission, which is very cool if you had not heard about it. So this is a European Space Agency mission. And the concept is this spacecraft is going to basically be waiting in a L2 orbit and essentially wait for a long period comet, hopefully dynamically new, maybe even interstellar object would be cool. And then once a target is selected, the spacecraft will then go and intercept the comet. And the launch is, I think the latest date is 2029. But this means that if the spacecraft can take, like if the comet will take, several years to get close to us, we could potentially find a target starting now. But it's important that we estimate these activity levels over this on the average 5-year timeline based on these initial observations. And this is important for the mission planning aspect because we don't want the spacecraft to get too close to the comet because there'll be a lot of dust. The spacecraft can be like destroyed a little bit. But also if the spacecraft's too far away, then a lot of the in situ instruments won't have enough material to really get those observations. So having the ability to forecast comet brightness over a very long time period is really required for this mission, and it's something that we've been focusing a lot of time on. So the main questions, I hope I provided you with sort of some background on the things that we kind of care about with at least this specific work. So there's three main questions that are really driving this. The questions are, so what are the drivers of activity when water ice sublimation is inefficient further from the sun? We want to know, is there any observable evolutionary differences between new and returning long period comets? Can we see how and why these comets are different? And then lastly, can cometary activity be accurately forecasted based on just initial distant observations? And so these first two questions I tackled in I worked on in a 2024 paper, and then we continued with that into focusing on this third question. So I'm going to go through both of those with you guys. So how we address these questions is using a data set from the LCO Outbursting Objects Key project, or what we call the LOOK project. So this uses the LCO global telescope network of 1 meter robotic telescopes. So there's 1 meter telescopes all over the world in both hemispheres, which means you can have nearly continuous coverage of these comets, where the only gap is when the comet is in the same direction as the sun. But otherwise, we can observe them. We started this project in August of 2020 to start observing. So we've been observing for a very long time. Another thing I want to say about the LCO network specifically is that one of the main things that makes this really unique and awesome is that these telescopes are all identical. So they have identical cameras, they have the exact same filter set, they have, so we have the uniform instrumentation, and then we also have the uniform processing, not just, the reduction, but also the photometric processing as well. So we're not comparing between different, systematic differences between different telescopes or different observers when we're comparing observations. So what we did was we essentially any long period comet that was discovered beyond 5 AU from the sun and was going to be traveling at least 1 AU closer to the sun, we added it to our list and we started observing it every 3 days in both G and R filters. So currently it is still going on, at least through this semester, and hopefully can continue on a little bit, but also we'll have LSST, so I'll talk about that later. So currently we're monitoring around 50 long period comets, which, depending on what type of science you do, seems like a very small sample, but for comets, this is very large, and it's been accumulated over, at this point, 6 years. So you can imagine it's been a long process to even get this many. We use the GNR filters. This was a specific choice because the G filter contains is C2 and C3 gas emission, which is a common byproduct from comets. And so the G contains this sort of gas emission, and the R band is mostly dust. So we can use G minus R color to also give us kind of an idea of the dust to gas ratio as the comets travel inbound as well. Yes. Yeah, so we're currently monitoring 50, and we include 21 of those in our initial study, which occurred using the first 3 years of data. So what we're left with, the thing that this project gives us that uh, no other data set has, is that we have really long-term, frequent, multi-filter, uniform observations. And it gives us beautiful light curves like these, which is over, this one I think is over 3 or 4 years. So that this comet, you can see this is being tracked actually from 9 AU all the way into, I think this goes into 2 AU. And this has hundreds of observations over several years. And this, and the uniformity of this allows us to see, how the brightening rate changes, if it does, or different changes in how the comet behaves without barely any scatter. Which you can see a lot of scatter when we start combining observations from multiple observers and from different surveys. So this is how we can really get a more focused idea of what is going on. So once we have this data set, we start by doing the traditional model. Let's see what the slopes are. Does this work? Are they any different? So we fit this value. So this is the N value here. So essentially, again, it's just think of it like the slope of brightening. We fit pre and post perihelion light curves separately. And we basically shifted the G value by the median color. So we had more objects. We also observed any changing G minus R color, but at these heliocentric distances, we did not see any changing color. So we just did a shift to get the most observations. But this particular comet here, you can see it only spans about 1 AU pre-perihelion, so it works okay. But what about like when we have much longer ranges? And what we found is that a single slope cannot be used across a large range of heliocentric distances. So in these, like in these examples, what we had to do essentially was fit multiple activity indices or N values at different points along the comet light curve. And this isn't like, oh, it's just like a fractional like difference. Like it is a changing, slope as the comet approaches the sun. So one of the main takeaways here is that this traditional model that we've been using for decades is really insufficient for these observations that are further from the sun. And so when we put all of these together, we see, you can see here, I've done the activity indices. So the slope for the heliocentric distance. So the span of heliocentric distance is marked by like the error bar there. And so if there's multiple for a comet, it'll just be the same color multiple times. And what we found is among the whole sample, comets brighten more rapidly further from the sun, so have a higher activity indice, a steeper slope, and then it sort of plateaus as the comet approaches the sun. And this does not negate the results that were from the past several decades. We still see that trend of those same sort of slopes within 3 from the sun. So this isn't like negating those original studies. It's just like in addition to that for these distances. Again, big takeaway is that a single slope can't be used, but also that they have a very similar pattern. So we looked at this and we thought, okay, we can see that the slope is changing and they all seem to be kind of changing in the same way, in that the index clearly relies on heliocentric distance in some way. So to try to come up with a new model, we looked at, okay, so let's make this, and we just actually literally take this activity index in and then change it to a linear dependence on heliocentric distance. So we went from N to this AB model. And I think so in the future, we're going to call these the first one like HN model. So the two free parameters are H, which you can think of as almost like its intrinsic brightening. A lot of times it has to do with its size for, for asteroids, it has to do with size. So you could think of it like that, just how it moves up and down. And then the bottom model we'll call HAB because there'll be three free parameters. I want to pause for a second now that we got there and said, like I said, the inner region closer to the sun is not negated, like does not negate past studies. What we found in our study was that basically for all comets in our sample, they can be the ones that spanned into the water ice sublimation regime can really be separated into those two regimes. So you have the long-term behavior outside of 3AU, and then inside of 3AU, you have much more different things happening because they're just a lot more active. So you have surges in activity due to water ice sublimation turning on. You can have seasonal effects as the comet travels around the sun, and also projection effects. So when the comet tail, how the comet tail is pointed and how that shows up in your photometric aperture can make a difference in what we see in the light curve. So for the purposes of this talk, and so it doesn't go on for eternity, we're going to just focus on this distant regime outside of 2.5 AU. We're still looking at the inside of 2.5 AU, but not for this talk. So when we actually looked at this new model that we came up with, we found that it works significantly better. So we have the old approach here on the left, where we have three separate slopes. And then on the right, we just have one model, but just uses this. It has an A value of 0.31 and B of minus 1.19. And you can see that's a pretty great fit. And it just is one model and not something that's in one set of parameters, not broken up into many. And it's not just this one comet. We found that for all of our comets, this fit much, much better. Here's some examples of 4 other comets in our sample. And you can see this captures the changing slope much better. So we found that this worked pretty well. So let's see if we can, does this tell us anything? Like I said before, we had a more shallow slope was for new comets, more steep. Can the distribution of these A and B values really tell us anything? So this is our initial distribution of the A and B parameters. And I will say this is also focused on pre-perihelion data as they're approaching the sun. And we found for the this tight zoomed in box here, these are the comets that have the largest range, heliocentric range. This I show here in this sort of the max heliocentric distance over min, the ratio, just because we're working in log space. So this is actually the largest difference rather than just heliocentric distance range, though it is similarly with just heliocentric distance range. So we found that those values are very tightly distributed around this. A is 0.37, B minus 1.58. The scatter in this broader distribution mostly is caused by basically it's poor constraints on much shorter arcs, as you can see here. We don't think that is genuine physical diversity, especially when we get into our other tests, which I'll talk about later. We also show in this little tight scatter a linear correlation as well, but I'll also just, in case it wasn't clear, this is a very small sample size, so that there's a caveat with all of these things as well. Another thing that we found that was surprising is at these heliocentric distance ranges far from the sun, we did not see any clear trends with dynamical age. Again, with heliocentric distance range, once you got above a certain like threshold that it could fit better. We also didn't see any clear trends with the H value, or you could think of like the size or the activity level, which is interesting. So another thing we have to think about is this model fits the data well. We can see that, but it also has 3 free parameters compared to the previous 2. And with 3 parameters, you could fit way more, right? There are more free parameters, make it easier to fit. So we wanted to know, are the parameters, multiple parameters for this object warranted, or can a more simpler model be sufficient? So we tested several different types of nested models based on the anchored values that we got from that original distribution. So we can take our A1 as the 0.37, B1 as 1.58, and we separated it into essentially fixing those numbers to the model and either both or one, and then also added 1 for the correlation. So that's what we called the model fixed AB, fixed A, fixed B, correlated AB, which is exactly what we think. We fixed the A and B models, so there's only 1 free parameter, just H. We fixed the A value, so A is equal to A1, and then B is free, and so on. And then the correlated AB, we basically link the A and B value via that linear correlation, but leave it with, so 2 parameters are free. And we found that the HAB model is always the best fit for our objects, but it also is even when we apply statistical tests, the Bayesian information criterion, which penalizes models for additional free parameters, it still shows that these additional parameters are warranted for better fit. So even though these simplified models, they have less parameters, the HAB model by itself is worth those parameters to get actually what is going on in the better fit. However, so now we know, oh, this is like really showing us what comets are doing. Can we use it for predicting? And as you may or may not expect, once we try to use this model for predicting, even though it is the best fit, it is not very good at predicting because it has too many parameters, so it overfits the data when there's not that much. So it's really a poor predictor to use for sure. And so we then tried our variants of the HAB model to see would those be better, even though maybe not for characterization of the whole curve, can it be better used to make these predictions? Which is what we found. You can see that here. So this figure on, we did a series of fitting based on different chunks. We basically fit different chunks of data going, adding more and more, and then projecting fit the projected model out to see which one was best actually doing the data with actually matching the data, even though it was fitting little data. That makes sense. So you can see here that purple line is not doing a very good job at all, and that's the HAB model. But some of these other models, like the fixed B, this orange dotted line, the correlated AB, and even the fixed AB is still relatively close, seem to be doing a better job. And when we look at all of these together, we can kind of get a roadmap for how should we be predicting brightness behavior in these long period comets. So this figure here, the bottom is the range of distance used for the fit, and then the y-axis is the mean difference in magnitude at this far right point where the ratio is 2. So essentially saying if we project using just this amount of data, if we project it out to where the ratio is 2, so the minimum is half of the maximum, what is the difference in the real data versus the projected data? I hope that makes sense. It's a little hard to explain. But how this comes is you can see, even when we just have that first little tiny bit of data, if you use the fixed AB model with only one free parameter, which is the red diamond shaped, it has a pretty decent fit. It has a pretty decent fit with just minimal data within most of the time, within within one magnitude of that, that's really good for us for predicting. And then we also have these sort of two parameter models. Once you have just a little bit more data, also converge quickly to something that's much more accurate. This also shows that the traditional model was not very good at predicting. It's pretty high up. And then the HAB model, like you saw before, it just is wild at predicting until you get a significant amount of data. I'd say at least like 1.5 to 2 AU of data, which they can take years to get to that. So to make that to cover that range. All right, cool. So now that we know, well, I guess let me just to kind of drive it home. So we can have this sort of practical takeaway here for predicting brightness behavior. So, as soon as we get data, we can start with this fixed AB model. And then once we have a little bit more, we can use some of these two parameter models to get a better idea, a more accurate prediction. And then once we have a significant amount of data, then we can do this full HAB model fit. So this is a roadmap that we haven't had before that we now have that is going to be really helpful in our future observations. So now to kind of go back to the science and the overall pattern that we saw in this sample. So this entire sample shows a rapid brightening around 8 to 10 AU. And I mentioned this earlier, this is consistent with the onset of CO2 sublimation. So you can think of it like the comet like turning on with CO2 sublimation. It really like ramps up and then kind of mellows out. So because CO2 sublimation is efficient in that range. But this is our entire samples behaving that way. So this suggests that maybe most long period comets that are discovered at these distances especially may be CO depleted, and their activity is actually dominated by CO2. And this is also interesting, like I said, because we can see in our discovery distances, we see that cutoff. So maybe it applies to not just our own subset, but many, many comets, many long period comets, if not most long period comets. So why might these be CO depleted in most of these comets? So there are a couple of possibilities. So there could be some thermal processing during the scattering into the Oort cloud. So in their formation regions, then there was scattering that placed them into the Oort cloud. And during that scattering, they could have had significant thermal processing. There's also an idea of in the Oort cloud, there can be a conversion from CO to CO2 by cosmic rays. Or maybe these objects are just formed in a different region than we thought that has a different type of chemistry. This figure also shows, though, that there's been several comets discovered beyond 10 AU. Right, we have C2017K2 was discovered at 15 AU, but it had pre-Covery observations much further back, up to I think 20 something AU. And then we have the largest known comet that we have, C 2014 UN271, which was active at 28, discovered active at 28 AU. So at those heliocentric distance ranges, CO2 is not an efficient driver. So for those, CO has to be active. It cannot be CO2. And fortunately, we can test some of this directly with JWST observations. So this gives us multiple test cases. So we can test this sort of A-B distribution and see what it might be telling us physically. So we do have these ultra distant discoveries, like I said, of the K2 UN271, and JWST observations of those comets do show CO sublimation. And those comets are not in our sample because K2 was discovered before we got started, and UN271 has a lot of outbursts and is just, and because it's so big, it's just its own special bird. Yes. But when we look at, but perhaps if we look at more of these comets that are discovered within this 8 to 10 region, maybe we will find that they are CO depleted, which is what we did find for the comet C2024E1, which had that same discovery distance, and we did find that it was CO depleted using JWST, and that's what this figure is here, CO2, and CO is over here. And you can't, it's not really there. Maybe, but with actually, nah. So we can, if we get more comets like this, maybe we can see if there's CO, CO2 abundances or these changes, if that has some sort of distribution in our HAB model between that AB distribution. It's also important to look at this value, like the CO to CO2, across varying heliocentric distances because it changes as a comet approaches the sun. So in doing that, we can also see what is at different points along the light curve, what are the different abundances and abundance ratios of these objects, and can we then build backwards and say, okay, if the light curve looks like this, then it probably has a ratio of around this. That would be really awesome to do with a big enough sample to look at using JWST, which we know is super easy to do. Yeah. So again, we can compare with the AB distribution, looking at some of these abundances, and also comparing with the actual light curve. And as many of you know, that pretty soon, Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, is coming online any minute now, perhaps. And they're going to discover, it's going to discover comets even further from the sun, so we can see much larger ranges, and there's going to be even more objects. So having more objects, larger heliocentric distance ranges, this is a perfect, perfect group and sample to do this type of analysis that we just did with Look. So this larger sample, we can hopefully tighten these population priors for the AB distribution. Maybe with a larger sample, we can say that that correlation is not really it, or maybe a different one. Maybe we'll see a like multimodal distribution somehow. I'm excited for more objects to look at. Unfortunately, because the look surveys that we did had a similar cadence of every 3 days that LSST is going to have. We have a really nice baseline for how to conduct this research already in place. Yeah, this sort of methods can be transferred pretty directly to that, which is nice. So just to summarize our here, the main points that I want you to take away that I hope you grasped is that long period comets actually brighten more rapidly further from the sun, and their rate decreases as they approach. And this cannot be captured by a single constant activity index. So that traditional model does fail when it's applied across large distances. We also introduced the HAB model. So that's an empirical 3-parameter model where the activity index is replaced by a linear function of heliocentric distance. And we found that this describes the distant light curve so much better and we found that there is a consistent clustering of our sample in the AV parameter space, which suggests that there might be a common driver for these comets, which we think could likely be CO2 sublimation for comets discovered in this 5 to 9 AU region. And this is supported by the JWST spectroscopy of like that one comet that was discovered at those distances that was CO depleted. If we can get more observations, we can see maybe a better picture. When it comes to predicting brightness behavior, so even though that HAB model fits the best overall, it has too many parameters, so it overfits with limited early data. But we found that some of these variants of that HAB model can do pretty well with early predictions. So we can even use the one parameter model with very, very limited data. With a little bit more data, we can use some of these two parameter models to get more accurate predictions. And then finally, with LSST coming online, we're going to have far more comets at far larger distances than we have before. So this is definitely going to tighten the population statistics, improve these sort of like anchor values, and then probably expand this in ways that we can't really see. So yeah, so while our understanding of comet behavior continues to grow, one of the things that I didn't get to touch on too much, especially because this happens a lot closer to the sun, is comets tend to always find different ways to surprise us, which is why we like to observe them. And doing studies like this can be particularly difficult, but again, yeah, that's what makes them fun to do. So thank you so much for having me. I'm happy to take any questions you might have.
Congratulations. So let's thank our presenters. So if you guys in the audience have any questions, please feel free to come up. Does anyone have any question?
And there's no stupid questions either.
So if someone is still thinking about their question, I have one. Like you mentioned, how LSST will be helpful to increase the sample size of the comets. And do you plan to use the LSST alerts to help with that, or like what do you expect from the alerts to help you? And congratulations for your talk. It was really nice.
Yeah, thank you. No, that's a great question, and that's something I met at the LSST at Latam. She's heard my rantings about doing comets in LSST because right now it's a little tough with the alerts because they're diffuse, more nebulous, and they're also harder to match with known comets because their orbits aren't as precise. So we're looking to figure out better ways to use the alerts for different things. We anticipate using the alerts mostly for more rapid changes in activity. So mostly like outbursts or an object that was not active at all that suddenly becomes active. So that's where we anticipate using alerts mostly. For this type of work, using the prompt products catalog to start, but then once we get the actual data releases, that could be a nice uniform package as well. But I mean, knowing myself, I don't think I will be able to wait that long to actually start looking at things. So yeah, great question.
Thanks. Does anyone have one? So Pedro here also has a question.
This is more of a curiosity of mine, but do you expect like LSST to reveal some new processes in comets at longer distances? Or are we done with the processes we know?
Oh, never. We're never done with the processes that we know. Especially, I'm looking forward to, even though based on what we see with this study, we might not be discovering as many ultra distant comets as that we hoped, which is also a little bit disappointing for the Comet Interceptor mission. But we will still discover many more at these ultra distances. And I'm really looking forward to seeing what might be happening there. A lot of these ultra distant comets as well, they're outbursting, which is an interesting feature. And it's one of those, is that how they start activity, or is that just how it happens until it's quiescent, like activity kind of overpowers it? So I'm looking forward to that. And then also seeing, like I said, these were discovered at, 8 to 10, like within 10 AU. But it's going to be, these types of comets will be discovered a little further away than this with LSST, right? Because in theory, so seeing sort of, maybe we can see deeper, maybe we can see when it's turning on, and that would be cool too. So there's lots of things that I'm sure the most exciting thing is something that we haven't even thought of. So, but hopefully that gives you an idea.
Yeah, cool, thanks. Any more questions from people at Zoom?
Did you have a question, Anna? I said you had your hand just up there.
No, my question was what the first Pedro asked.
Okay.
So covered. Do we have anything on YouTube?
I don't know. Yeah. People on YouTube are kind of shy. So. Yeah, I don't think so. So, if we don't have any more questions, I think we can wrap up. So let's thank our speaker again. So, thank you.
Thank you.
Great. Thank you guys so much for having me. Have a good day.
Bye-bye.
Bye-bye.
Have a good day.
Bye-bye.
Bye-bye.